Let's write out the equation then. When you are, that was really good chocolate. Had it last night. It was very good. It was really good because it was in thirds. So I had a piece, my wife had a piece, and my father-in-law was over last night, so he was able to have a piece. He thought it was really good. Anyway, so sometimes what will happen with the last bit in 14.5 is that you'll be given a maximum and a minimum point, and you have to come up with the idea of writing out the equation then. Now, the easiest way of going about doing this is to, first of all, plot it. Look at what it's doing. That way you're going to be able to decipher whether it's going to be a sine or a cosine graph, and then how complicated you want to make it. So when we do this, we're going to draw out, like we have before, a very simple plot line. We have a maximum at pi, and a minimum at 3 pi. I knew that somewhere in between the maximum and minimum was going to be one extra piece no matter what, so I just put that spot there, which is going to be at. Now, if it's at pi and 8, that means it's going to be up here at 8. And if 3 pi and negative 8 means it'll be down here at negative 8. Means my curve is probably doing this. Are we okay with that?
How do you know the curve is doing that?
Because it goes from left to right. So, just like when we looked at the graph, the first thing we're going to figure out is what our value of k is. Our value of k is always going to be the average of the y values. Well, what's the k value here? 0. So I have a k value at 0. All right. Now I need to start figuring out whether I need to make this a sine or a cosine graph. So what I want to do is figure out what this graph did at the origin. So if I went from a maximum to 0 to a minimum, that means going this way, it would be at a 0, and then it would be another minimum this way, correct? So that means it went up, down, and then it's going to come back up here, isn't it? So is this going to, if I start here, is that going to be a sine or a cosine graph?
Sine.
Sine graph. Plus I know it's a sine graph because look how many times I crossed my k value. I crossed over it 4 times. No, don't remember, sinusoidal can be sine or cosine. Okay. So I crossed over it 3 times, which means I'm going to make it a sine graph. What's my a value?
8.
My a value is 8? Yes, sir.
Can a tangent graph also be?
We're not doing any tangent. Tangent graphs are non-continuous. These are sinusoidal graphs are continuous.
Okay, yeah. I wasn't sure because like on the sheet, the packet that you gave us yesterday, there was a tangent graph, and I wasn't sure.
Was there one on there?
Yeah, that was a tangent graph.
Oh, okay.
So I wasn't sure how you're supposed
I'm not going to make you write them off though.
All right.
So I knew that my a value was 8. All I have left now to figure out is the period. So how far was it from horizontally from here to here?
2 pi.
2 pi. So I take 2 pi, and what do you do to that? Double it, and you get 4 pi. And what do I do to figure out? Very good. What's my value of b?
2. 1/2.
1/2. My b value is 1/2. Yes, sir.
Why 2 doubles 1 high?
Remember, between max and minimum is always half your period. Double it. And then you can figure out what it is of pi, 2 pi over b. So now you have your b value. So we said it's going to be a sine graph. Y equals 8 sine 1/2 x.
Whoa, that's easy.
Okay. Remember, what we did here is we used the path of least resistance. We went backwards to figure out what was happening at the y-axis, to figure out where the intercept was, to decide whether or not it's going to be sine or cosine. Because couldn't I have also called this a shifted cosine graph?
Yes.
And that's more of a pain in the butt, isn't it?
Yes.
If you ever want to shift things left and right, there's more involved. Path of least resistance tells you not to do a horizontal shift. Work yourself backwards to the vertical. Excuse me, and see what happens. It's much, much easier. Okay? Do another one.
Wait, why is 3 pi your minimum? Oh, no.
It's given to
That
you.
was a stupid question.
No, it's not.
I just realized why.
It will be given to you.
Yeah.
Okay.
Shut up.
It'll say A is a max, B is a min, things like that.
Are we gonna go over that thing?
We will start going through it, yes.
Chillax videos. Take a chillax.
I like that.
So I have a minimum at 1, -3, and I have a maximum at 3, 7. So it's going to be doing something like that. I want to first of all figure out where my K value is. The K value is always going to occur at the halfway point of the Y values for the max min. Yes, ma'am. It's not. It's okay. So what's 7 and -3?
4.
Yeah. 4. What's half of that? 2. So my K value is at 2. So I know K is 2. So at 1, it was a minimum at 1, so it had to fall. Then it went through 0 at 2, and it hit the top here, which means it's going to come back down here, don't you believe?
Right.
Which means it went to here, somewhere along the lines. But that meant that it had to have been through a 0 at some point. So that meant it had to have come down through here, gone back up, and come back down.
Sign.
Good. It's going to be a negative A value because what direction did it go first? Down. And notice that between your maximum and minimum, it goes 3, then a 1. That meant those are 2 of those spots, the maximum min. That means somewhere in between them, it had to go between the 2. And it's nice that you're going by 1s again. You can start to figure those patterns out. So we know that the A value is going to be negative. And how far is it from 2 to -3? You just said, right? What was it? -5. Very good. And now to find my period. How far apart is 3 and 1? 2. Double it and you get 4. So we're going to set our period is going to be equal to 4. Pi over 2. And do you have enough information to write it out?
Yes.
Yes, sir.
What was your process to determine the sine graph?
I worked backwards to the y-intercept.
As far as like
Yeah. Because we knew from between here and here, minimum to maximum, it has to go through 1. Since that distance is 2, half of it has to cross the middle. And if you remember when we did our graphs, our chunking, we had out, out. So we had 1, 2, 3, 4. We always had 5 points. That's how we start to count through. really easy, or I should say easy, really nice way to remember how to do that. So your final answer then y equals -5 sine of pi over 2 x and then plus 2. Just don't put the plus 2 in a parenthesis, you're going to be fine. Because then it would make a wedge. And that's no es bueno.
Wait, say
That again, this way.
that again. What did you just say?
I said that why don't we put it as in parentheses the plus 2, the x plus 2? Because then it would be a horizontal shift. Even though it says x then plus 2, our h values were always thrown in parentheses. So just don't try to do this with no h's. It makes your life a lot
Is
easier.
that why a lot of the time it's 2 plus?
Yeah, exactly. That's a good point. If you wrote it like that, it's fine. Means the exact same thing. And you actually will see it written like that more often, especially with your a values. We okay on that? All right. Now, what I want to show you guys here is another thing about sinusoid stuff. When you start looking at word problems about when to use a sine, when you're going to use the sine regression, the sinusoid regression, because there's a button for that, in case you haven't noticed it yet. Yeah. There's a sinusoidal regression. And it'll automatically put it as a sine graph for you. When you're looking at sinusoid graphs, those are things that repeat themselves over and over again. Think about snowfall, rainfall, temperatures, average daily temperature. You have more snow in the winters than you do in the summer, so snow, unless you're in the south. But then it's still summer and it's still winter. It's just the dates have shifted, like a cosine graph. When you start using a sinusoid model, if it doesn't tell you what to use. Sinusoid modeling, when you're using like L1, L2 for your regression, if I'm looking at, just scrolling ahead real quick, if I'm looking at average daily temperatures for anywhere. Temperatures start low, they work their way up, and then they work their back down low. They replicate that over a specific period, a year's period. That's when you start to look at, okay, that's going to be a sine graph versus an exponential graph. Temperatures aren't just exponentially getting hotter. They still replicate themselves through. Same thing with like tides. Tides go out, tides come in. Yes, sir?
What if like you have the repeating up and down, but it is going up? Would it just be okay?
It's an x, and that's kind of what's happening with global warming. It's still a sine graph as it's going through because it's oscillating, but the oscillation is oscillating in an upward movement. I don't know if that's
What does that mean? Like a diagonal.
Yeah,
Like K equals Y.
I'm sure there's something. I'm not exactly sure how that's called, but I know is that kind of what you're getting at? Yeah, it's still replicated temp. That's an average of moving upward. Yes, ma'am.
She's really mean.
She's saying he's really mean and she's kicking his desk.
You didn't hear what he said, he bullies with words. He does.
And she bullies with fists.
I'm not the savage.
Oh, he's bully.
Hey, remember when that
Anyway, so what happens, guys? What happens here is don't read too much into it, because temperatures are going to fluctuate, but temperatures go up, temperatures come down. You're worried that they always be a constant value away from some K line.
Wait, okay, so it's still a sinusoidal graph even if it's not constant?
Because if you're looking at temperatures aren't always going to be, as you graph over something, temperatures aren't always going to be equidistant from that K line. There's going to be fluctuation to it. But the idea that in January it's cold, it gets warmer, then it gets cold, then it gets warm. Well, it doesn't get negative, but it gets warmer and cold, and it just oscillates throughout the months. Think sinusoidal when you see something in terms of an annual, like rainfall, snowfall, things like that. That's probably what they're looking for you to do. That's a little hint. Yeah, and sound waves do the sound graphs like that. Anything that replicates itself through. Yes, sir.
In instances like rainfall, would your K line be the average?
Yeah.
For
Yeah, because it's not going to be a zero. And you're not going to have negative rainfall because it'd just be a vertical shift. And that's kind of what happens. Yes, ma'am.
What is the sinusoidal button?
I think it's called. Yeah.
there's
There's always a button.
Sine reg.
No, that's not
Oh,
it.
yeah, we got that for that.
That's not it. It didn't work for me. What did you do? It says error singular matrix.
Because that means your stat sucks all this
you
stuff.
go to
Sine reg?
what are you doing?
Stat calc, sine reg.
That alpha or alpha. What's that alpha?
Sine regular or sine? No, is there a deal with that?
Wait, how do we get to
Where's sine?
Oh, I think that's good too.
Nice.
It's only January?
I don't know why it's that. Let me figure that out. Give me a second to figure it out. That should be it.
That was a while ago, though. I think it's like one of the earlier ones. Like when they first come out.
Did you change something?
So the language in the Netherlands.
Wait, yes.
We'll go back and figure that out in a second, but I want to talk a little bit else about some of the stuff on that packet. So one of the things that we really haven't had a chance to talk about yet is when you're looking at graphs, how are you going to be able to tell what type of a model it probably is looking at? One of the things you have to remember is when you're dealing with polynomials, if you have a third degree polynomial, up to how many changes in direction could it have? 2. How many zeros would it have? Could it have? 3. So when we start looking at stuff like this, if I'm looking at number 1, I see that I have 1, 2, 3 changes of direction, which means it's going to be a quartic. Okay. Now be careful. When you have a quartic, that means it's a 4th degree polynomial. Remember when we did polynomials back in the day, some of our polynomial graphs might have had imaginary solutions. So that's possible to have a quartic graph that looks quadratic. So just remember, here you'll be able to definitely tell it's going to be quartic because it changed direction. What is 8 going to have to be then? Quartic. Okay. What about 15? Cubic. Another reason why you can tell it's going to be cubic is because how many times does it touch the x-axis? You have 3 zeros and 2 points. Yes, sir.
So how do you know that a cubic could be proportionate with an imaginary
Show me. When you, with a lot of these things, you're going to have, when you had a cubic one, you could have imaginary answers, but still show the change of direction. Remember how sometimes cubics had 1, 0, and you had plus or minus 2i? That could happen in a graph that looks like this. Where you had the 1, 0, and this was an imaginary. That's where you'll see that. So when you're just looking at the graph, you basically count the terms. All right, count the terms. Now, the other thing is that how do you tell the difference in a graph versus exponential versus logarithmic?
Up or down?
What's the difference?
Yeah. What happened? One of the nice, easy things to remember about logs, logarithm graphs, and this is you're gonna think this is really stupid, but I think it's awesome. if I just type in log x, and I look at my graph. Oops. Oh, again, remind me to show you a trick with your graphs.
Yes, sir. Your window rate, if you put 1,000 as the scalar,
I didn't know that.
10,000.
I mean, it's just a small problem.
Correct? Oh, because you have the list up. You still have the graph from the list up.
I've only seen it because.
Did I mess up that?
Yeah, your graph.
Oh, my max and mins are backwards.
Second plus 722.
Yeah, I should, right? There. So don't worry about my stat plot. Well, I was turn it off. So if I look at that, remember logarithms had vertical asymptotes. Exponential functions had what?
Horizontal.
They had horizontal asymptotes. If I do e to the x in another graph, e to the x had a horizontal asymptote, log had a vertical asymptote. Why do logs have vertical asymptotes? Because what are logs made of?
Trees.
And where do trees grow?
Trees.
Oh!
What if you chop it down?
I'm pretty sure trees grow on the flat ground, actually.
But they grow upward, like a vertical asymptote. So logs have vertical asymptotes.
Unless you live in China.
Remember that was it.
Wait, what's the other one you said?
Minus h.
If you're in China,
There's always one. But it's always increasing. So that's another way to remind yourselves when you're looking at, like on number 9. That's logarithm. Okay. It's a little trick. Now, getting into the other stuff that's on here.
You get stuck in the ground.
Now, when it gets into these things, when we did this about looking at our lists, trying to decide whether it's going to be some form of polynomial versus exponential, power, logarithmic, or sinusoidal, the quickest thing to check yourself with is to do an L1, L2. Okay? Now I'm going to show you a nice little trick. We can do L1, L2, or we can check finite differences. Finite differences will work if it's going to be a polynomial. Remember, that means you're subtracting the differences going through however many times that tells you the degree. Only works for polynomials. Won't work for exponential or logs or anything like that. But I want to show you a trick with number 24. Let's put 24 in our L1, L2 real quick. I'm going to show you what happens. All right, so I go to my stat, edit, L1. 24 we're doing, so it's 1, 2, 3, 4, and 5. Oh, I know what I did. Did you guys get those values in? Okay, let's go do our stat plot. All right, turn mine back on. And then I'm going to hit my graph. Now, at this point in time, you guys would have had to have adjusted your window. I just found out that there's a button that'll automatically fix your window.
What?
Yes!
No.
Yes!
No.
Yes!
No.
What is it?
Zoom 9. I didn't know it worked. I didn't know. I learned today.
Well played.
And how long have you been teaching with TI-84 pluses?
10 years.
10 years?
Wow, you gotta be like 90 years old.
Yeah, I know. I always like.
We can do
So let's try 20.
I haven't tried to get Mr. Rush.
Don't even show. So now, this is what the graph looks like. I hit that stat plot and it automatically changes the window. It's quartic. Why is it quartic? Because it's wonderful. It's most wonderful.
Time of the year.
So, we okay if I say this has got to be quartic? All right. So, how would you find the formula if you're saying that's going to be quartic?
24.
24. Stat. Calculate. Quartic. Is there a button for it?
Yes.
Number 7.
Is that quartz?
That's so funny.
Show me 7.
Wait, which
Quartic.
why is mine negative? Wait, what'd you get for E?
Yeah, mine's not that.
Negative
Stuff.
7. I think.
I got negative 3.79.
Yeah, not your.
That's good.
Oh, you messed up.
It might be 20, it might just be doing 20.
Negative 11, 2, negative 6, 5.
Negative 6, 3. It's 4. It's literally 6, 4. No, negative 6, 5. But 5, negative 16.
Oh, I did negative 26, not negative 16. Sorry. Oh well. Now, when you look at some of the other ones, let's flip over to, which one was it?
Wait, so then do you have to like write?
No, I just state what it is. I mean, if you had to write it, it tells you your A, B, C, D's, and E's. So you just write it out. Let's look at, what was the other one I wanted to look at on here? What number was it? Look at 28 real quick. Let's do 28 in the regression in the calculator. So 5. So that's what that is. Graph it. I gotta adjust my stuff.
That new shortcut is so nice.
Isn't that shortcut nice? I'm sorry I didn't know that before, so don't tell Shimki.
Wait, where is Shimki? Yeah, no one tells Shimki. It was funny. Where is Shimki?
What does this look like it's doing?
Exponential.
How could you be sure it's exponential?
Is that more so to it? And it's going up.
Or, what's the other one?
It's increasing at a faster rate.
It's increasing at a faster rate, but go back to your stat. Let's make an L3 and do natural log and plot it against it. Because if I do the natural log of my...
What number are you doing, Mr. Murphy?
This is 28.
So you do natural log for exponential.
Yeah, this is one way for you to be able to tell if it does work out. Because when I graph it, oh, I might have to readjust the window. I wonder if I zoom 9 now, it'll work.
It does.
Oh, I didn't turn on the stat plot. Yeah. Yeah.
There you go.
All right, man.
Mr. Murphy, I forgot how to turn on that phone. Never mind, I got it.
Oh, I got to turn on. Hey, good luck. What's that?
Do you have to turn on the second one?
Yeah, I got to turn on the second one. I forgot to make it an L3. That's why.
How do you turn on the second one?
And then I use zoom 9, and it. It looks linear now, the red one. Did everybody get that to work?
No.
How do
Okay.
you do that?
So to do what, the graph?
Yeah. No,
Okay.
do that.
It like
The natural log.
All right, so when I go back to do natural log, you're going to your stat, edit, and you're doing that in an L3. You just do natural log 5, natural log 5.3, and so on. You're just typing that in.
Yeah.
You don't have to do it separately. And then you go to your stat plot, turn on the second one, hit enter on 2, and then just hit enter again. But then you have to change the Y list to L3. You scroll down and just overwrite it by hitting second 3.
How do you know to do natural log?
Because I'm checking to see if it does look like it. I mean, to me it looks like it's going to be exponential. If it does become exponential when I look at the graph, the other graph versus when I do the natural log should look linear. That looks linear to me. Okay.
How do you
And then,
go to natural log 3? I mean, sorry, not log 3. Do the third list.
second 3.
Are there going to be cases where it's like we check it and it's not?
It shouldn't. It should work out for you. I mean, exponential is pretty quick to see. Okay. Excuse me. Let's take a look at 36, and in 36 it's talking about use finite differences.
What does first order, second order?
First degree, second degree, third degree, fourth degree. That's what that means. First order, second order means first degree, second degree, third degree. That's when you're trying to find finite differences. Using finite differences is great when you have polynomials. Finite differences won't work when you have exponential or logarithmic. That's when you'll probably wind up using your graphs a little bit more. For some of these, when you're doing finite differences, it works pretty fast. Here's a 0, -2, -4, -6, -8. -2, -2. Hey, look at this. -2. And guess what? -2. Was that the devil?
Yes. Close. Diablo. Third.
No. How many times did I have to do it? What's the degree? Squared. So I use a quadratic regression.
That's the biggest.
You can do linear, but you should be able to see linear really fast. What's that?
We didn't do these. We didn't do it. We didn't do it.
It's much easier to do.
Oh, this, when we were doing it, we did it wrong. That's what I was like.
Oh, I got you. Yes, sir.
Yeah, we did it wrong.
It's just, yeah, it's in there.
Oh.
It puts it in the standard form.
Like we got the right answer.
Yeah, there's different equations when you get to the other problems, and that I was helping at least girl from a third hour on this earlier. When you get into these guys where it's telling you to use the different equations, when I'm looking at quadratic regression, it's telling you what it is, but it also gives you 2 zeros. And that's when you'd use your a, x minus p, x minus q, substitute in and solve for a. That's the other way of finding that, when you're using the zeros. Okay? That's one super easy way of doing it. Yeah, Bella? What's up?
Okay, goodbye.
Hold on. Yeah, Bella. Finish working on this.
Nice.
So if I'm looking at quadratic regression, basically what I'm doing here is this. If it wants you to write it out another way, the other way that this works, whether it's quadratic, cubic, quartic, doesn't matter. It's going to be y equals a something something. This is for quadratic. That would be cubic. That would be quartic. You're just using the zeros. So this would have been x minus 4, x minus 6. And then I would just substitute in one of my other ordered pairs to solve for a. Does that make sense? That's what that means. For polynomials, that works for any polynomial problem, whether it's quadratic, quartic, whatever. It will always work by using the 4 zeros, 3 zeros, whatever it is, because once you know your zero, you know your term. And then you're just going to solve for that constant a value up front, and you're done. Is that all right then?
Yeah.
It's a really nice way of doing it, especially if you have zeros. Clean ones. Okay. Yes, sir.
We look at number 40.
Sure.
Wait, this one, how did, what happened to get everything figured out there?
What's that? Then you'd have to work with the regression formula, just hit the button on the calculator. I don't know. See you guys. Good luck.
Thank you.
When I'm looking at 40,
It'll never be the
isn't this just oscillating up and down? What would that be? None.
Is there any, that's it?
It'd be sinusoidal. Does it ask you to write the formula?
No.
No.
It has to do like the first.
It would be sinusoidal because of the oscillation. It just oscillates between the two values. So every other one is boom, 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 boom.
Okay, I didn't know if there was anything else.
Nope.
here. Okay.
No, that's it. Yeah. no.
Wait, if it asks you to write, would you do based on
This one you could probably write with your HK thing pretty quick because you just have to figure out which one's the maximum and min. Oh, it's pretty easy. Which one's the maximum? Which one's the min? Which one's the max? Maximum's at 8, your minimum's at 1. You could probably figure that out really quick. All right. Yes, ma'am.
Is this whole test calculator?
Yes.
Woo!
Awesome.
Why'd you still
Oh,
fail?
you get something.
The people that are on the team that I'm in, there's 4 of us, if I can count 4. There's a Melissa, a Jenny, a Jeff, and a Joe.
Which one are you?
I'm the Melissa. I'm doing a team relay marathon on Saturday. It's my very first race I've ever ran at U of I. At U of I.
You never ran.
Never ran a race in my life. It's the first time I've ever raced.
I thought you meant you never ran before.
No, I run.
Yeah, you were just bragging about your.
And then I'm running the first leg.
Hey, what is it? Good luck.
How much is it?
That's a nice
How much
shirt.
is the
Where'd you
first
get it?
leg?
6'8" or 6'9".
Did you get it custom.com?
No. We know a guy that makes shirts. Yes, sir.
So how tall is this person?
Who?
You said you're running the first leg. How tall?
That's good.
So yeah, the what's going to happen tomorrow is that we'll go over more of this stuff and kind of roll basically problem by problem, just kind of knock it out. All right. Yay!
So you went to homework some last night or?